Hello, my name is Matthew Boyd, and I'm a research engineer at the National Renewable Energy Laboratory. I work in the Building and Thermal Sciences Center and focus on thermal and solar energy systems modeling. This presentation is on the updates to the physical parabolic trough model in the System Advisor Model software package, or SAM for short. The physical version of this parabolic trough model is based on analytical as opposed to empirical relationships, with the physical model being more flexible. This work was under the SMART project, which is an acronym and was in conjunction with Solar Dynamics of Broomfield, Colorado. The PI was Mike Wagner at NREL. Industry overseer was Kyle Katke at Solar Dynamics, and the technical assistant was NREL's Ty Nisus. The impetus of these model updates was to facilitate modeling a direct molten salt system where the heat transfer collection fluid is the same as the storage fluid. A brief overview. There were a few bug fixes, both prior known and a few newly found ones. Sections 2 through 6 were communicated needs from our industry partner Solar Dynamics. And item 7 are other related SAM updates, quality control, and documentation. Shown are a few of the early bugs that we addressed. All of these bugs resulted in relatively minor differences in the yearly projected energy, less than 1%. Script templates. SAM has built-in functionality for scripting model runs, and this was employed to demonstrate and facilitate the usage of these newly added features. The scripts are in the LK language, which is very simple to learn, and are included in the release and can be found in the listed directories. The scripts are needed for using the new interconnect definitions, unless you are keeping the defaults. With that said, any scripting that SAM supports, for example, Excel, VBA, or Python, will also work just as well. A large part of the update to the physical trough model were making the system piping design more customizable for both performance and economic reasons. Heat transfer fluid temperature and pressure are now being reported as absolute values instead of just differentials, which aid in pipe sizing. These values were calculated at design conditions after the system reached steady state. This new analysis does not take much time to run, but can be disabled using a parameter flag if so desired. Shown here are new parameters that were added that relate to pipe sizing in the field. All of these parameters are scriptable and currently are not accessible in the user interface. Their default values, however, result in equivalent performance and the same modeled values as the previous model version. Similarly, shown here are new parameters that relate to the pipe sizing in the thermal energy storage system and the power block. The first parameter also adds a new control for how the field is bypassed during times it is not producing. If the has hot tank bypass parameter is set to true, the heat transfer fluid coming from the field is routed through the cold storage tank instead of straight back out to the field. By doing so, the cold tank acts as a thermal reservoir and reduces the amount of auxiliary heat energy needed to keep the fluid above its freezing temperature. A new set of parameters that were added to the user interface are the minimum and maximum velocities of the heat transfer fluid in the cold and hot headers. Before, the cold and hot headers were grouped for this sizing, but it has been differentiated in order to allow more granularity in selecting the diameters for the different type and different cost piping materials in the cold versus the hot headers. These new parameters feed a completely new sizing algorithm that better handles edge cases and preferentially selects smaller diameter pipes when the smaller and larger options are equally out of range. The algorithm also allows more diameter changes for the hot or costlier pipes, sizing those first and stopping when it hits the user's selected limit on the number of total diameters. The option to use pipe section specific loss coefficients in the test steam generator system has been added. This is another option in addition to the existing single loss term that encapsulates the entire piping pressure loss in these systems. These pipe section specific parameters are lengths and diameters for pipes and minor loss coefficients for fittings. The lengths, diameters, wall thicknesses, and number of expansion loops are being reported for the entire field, thermal energy storage, and steam generator system for post-processing by the user. The HDF properties in each of the pipe sections are also reported at steady-state design conditions. The example scripts also have checks for reducing wasted simulation time. If scripting, the prior generated output files can be modified and used as input files for the next model runs to even more granularly tune the model, pipe section by pipe section. These values take the place of the auto-size values calculated by the program using the operating conditions and the desired min-max flow rates. Interconnects. Interconnects are what connect the different pipe sections and heat collection elements. They are assemblies of expansions and contractions, elbows, valves, T's, other straight pipe sections, and or flex hoses. The interconnects and their effects on pressure drop and heat loss were originally hard-coded in the model. Piping between solar collector assemblies were treated as straight pipes of the shortest length with additional losses from a typical combination of valves, elbows, and other joints. Now all components in every interconnect can be customized. To reiterate, interconnects are assemblies of components. The pressure drops of the interconnect components are modeled according to their type, using minor loss coefficients for fittings, the Darcy-Weisbach friction factor relationship for piping, and an empirical model for flex hoses. Heat losses are only considered for piping, which was the recommendation by our industry partner, as they are relatively negligible. And this piping heat loss is calculated according to its outside surface area and a global heat loss coefficient, just like before. The interconnects are defined in two different input files, one for the interconnect components and one for the assembly of components, or interconnects themselves. The interconnects do have default values, however, that capture the previous implementation, and using these defaults thus results in the same modeled outputs. Shown here is the file defining the interconnect components with an example interconnect shown in the upper right. Each component is given a short name, description, a minor loss coefficient if applicable to the type, an inside diameter, length, and a type. As shown, different components of the same type can be created. The components are combined into interconnects in the file shown here. Interconnects, again, are just assemblies of the components defined in the previous file. The components for each interconnect are designated by their short name and delimited by a dash. The number of components in the third column is for error checking, as listing the components can be tedious and maybe error prone. The order the interconnects are in is important, as this designates their position in the loop, as shown on the next slide. The interconnects are defined in flow order. For the inlet, first half of the loop, crossover, second half of the loop, and outlet. The inlet interconnect, for this example at least, contains everything from the weldolet on the cold header pipe to the T connection. This is circled in red in the upper right and defined by the first interconnect definition in the spreadsheet on the left. In this example with 8 SCAs, there are 10 interconnects. On to flex hoses. Flex hoses are used in place of regular pipes when the connections move, like for SCAs, with an example shown on the right. Their pressure drop is dependent on their size, like regular pipes, but also on their type and how they are flexed. Flex hoses have not been previously modeled in SAM, as connections between SCAs had been treated as straight pipes. A new relationship has been added based on a modified Darcy-Weisbach equation, shown here. The flex hose type is most closely related to the roughness in a regular pipe. Traditionally, there are three main kinds, and they have different friction factor versus Reynolds number relationships, as illustrated on the left. The reason flex hoses cannot be modeled as regular pipes is that the corrugations generate vortices that affect the flow in the center area. They behave like regular pipes until a Reynolds number of about 80,000, at which point the friction factor can double as these vortices grow larger than the outer pockets. In a typical studied trough plant, the Reynolds numbers can reach into the second transition zone, so this effect should be accounted for. In SAM, flex hoses are modeled like any other pipe until a Reynolds number of 6,000. This includes the standard laminar flow relationship and an iterative solution of the Colebrook relation for the first turbulent transition region. Above 6,000, the flex hose is modeled as one with average characteristics, which happens to be a type of annular corrugated hose. Above a Reynolds number of 6,000, the friction factor is kept constant until a second transition zone, which is around 80,000, depending on the flex hose. Between this number and a Reynolds number of about 500,000, the friction factor has a linear log-log relation with the Reynolds number. And above this, the flow enters another steady state regime termed the high velocity zone, and the friction factor is modeled as a constant again. The flex hose model employed here is empirical and uses public measured data from one of the largest flex hose manufacturers. Shown here is a plot of the friction factor versus Reynolds number for 4 different hose diameters for a flex hose with average characteristics. As can be seen, the Reynolds number for transition points between the constant flow regimes and the transition zone depend on hose diameter. This functional relationship between pipe sizes was inferred as a natural logarithm with relatively good agreement. The friction factor at transition points as a function of the Reynolds number is more apparent in the data plots and is modeled as a linear log-log relationship with different model fits for the low and high transition points. The complete model, with example results shown in the colored plot, is a very good fit to the measured data. The original data plot is shown both to the right and the bottom of the colored plot for easy comparison. The effect of bending has not been included in the model, as this was outside the scope of the project. However, adding this relation should not be too difficult. Determining the angles of the hoses, or discretized hose segments, according to the design specifications, could actually be the more difficult part. Beyond the piping changes incorporated in the new release of SAM are changes to the integration between the field and the thermal energy storage power block. The field, or solar collection section, is now decoupled from the TESS and power block, or generation section. This means that the solar field mass flow and heat transfer fluid temperature do not dictate power block mass flow and HTF temperature, and vice versa. The diagram on the left is the default parallel plant configuration. Parallel meaning that the field flow is in parallel to the TESS and power block heat transfer fluid flows. This was the only prior option, and it could be used for either indirect or direct systems. The new series option is on the right. This can be used for direct systems only, where the field HTF is the same as the storage fluid. Parameters have been added to customize the control of this new series configuration. When the test and power block are bypassed, the field HTF can either be routed directly back to the field or through the cold storage tank. Before, the only option was direct back to the field. Again, this uses the cold tank as a thermal reservoir and reduces the need for freeze protection energy during low resource or at night. As also mentioned before, the sizing of each of the individual pipe sections can be customized. The effect of series storage tanks and using the cold tank as a thermal reservoir can be seen in the example here. The top set of plots is for a parallel configuration, and the bottom set is for a series configuration. For the same resource, the HTF sent out to the field during the night is much warmer during the night. If you look between the peaks in the very bottom plot, this significant potential energy savings is now being captured in the SAM model. Lastly, some remaining updates pertaining to the user-defined power cycle and testing and documentation. The power cycles in SAM can be customized, effectively using a model created in another piece of software. The other model is run at prescribed input conditions, including parametrics for the heat transfer fluid entering the power block, the temperature of the flow rate of the HTF, and the temperature of the ambient air. These values are put in the three tables on the left, and SAM interpolates them during simulation to get arbitrary model performance. Inputting user-generated data into the three different tables on the left, however, was a bit cumbersome, so a new format was made, shown on the right, which is now just a single table. 6 total low and high values for the independent variables are input at the top, just like before. If you want to generate parametric model inputs for direct copying to your modeling program, you can just input the number of levels for each variable and press the new Generate Inputs button at the upper left of the table. After using these inputs to run your model, you can just copy and paste the values right back into this one table. But as long as you follow the same design of experiments design, you can input the model outputs in any order. Checks are also in place for detecting the correct set of values, for missing values, and for other common user input errors. Open source SAM is moving to require unit tests be created for all current and newly added compute modules. These serve as automated code integrity checks, verifying that model values are in agreement with expected results. They also help catch unintentional side effects of other code modifications. As such, a unit test for the physical trough model has been created. Help files related to the physical trough model have been updated for the October 2018 release. These include definitions of all new inputs and output variables, as well as descriptions, equations, and diagrams of the new functionalities. And that wraps it up. Thank you very much for listening. I hope these new features can benefit your modeling applications. If you have any questions or comments, please send me an email at matthew.boyd@nrel.gov. I am very interested in your feedback and happy to help however I can. Thank you for your time.